Hello, I'm Ryan from the University of Illinois, and I'll be talking about how dynamic range compression affects noisy signals. People with hearing loss, like me, rely on hearing aids to communicate, but hearing aids don't work well in loud, noisy places like restaurants or parties, where we need help the most. They often amplify noise or cause distortion, making it harder to hear. Dealing with noise is one of the most difficult challenges in hearing aid signal processing, and engineers have been trying to improve noise reduction performance for decades. But there's one problem that hasn't received much attention from engineers, and it might be one of the reasons that hearing aids struggle in noise: an algorithm called dynamic range compression. Every modern hearing aid uses dynamic range compression to keep sounds at a comfortable level. Most sounds need to be amplified to make them easier to hear, but some need more gain than others. When sounds are especially quiet, the hearing aid will increase gain to make sure they're audible. When sounds are too loud, the gain will go down so that the sound isn't painful. This level-dependent gain reduces the dynamic range of the sound to match the range of the listener. Because the gain of the hearing aid changes based on the loudness of the signal, dynamic range compression is a nonlinear process. That means that a change in one sound affects how all the other sounds are processed. Let me demonstrate the problem. Right now, you're hearing my voice with exaggerated dynamic range compression applied. This severe compression keeps the sound level close to constant. If there is a sudden loud sound, then the hearing aid will turn down the gain, meaning my voice will also get quieter. Let's hear that again, but this time, through the magic of pre-recorded presentations, you won't hear the pot, only my voice compressed as if the pot were there. My voice dips in and out, making it harder to understand even without the extra noise. Hearing researchers have known about these problems for decades, and there have been dozens of papers that document them in both simulated and real hearing aids. Because the effects are nonlinear, they can be hard to quantify, but researchers have found 3 ways to measure the interaction between compression and noise quantitatively. First, if 2 uncorrelated signals are compressed as a mixture, they become negatively correlated with each other at the output. Second, dynamic range compression has a weaker effect on the dynamic range of a signal when there's background noise than when there isn't. Third, compression can change the long-term signal-to-noise ratio of a mixture, sometimes making it better, but often making it worse. Most research on dynamic range compression has been empirical. We put some signals into a hearing aid and see what comes out. But to really understand the problem, we need to approach it mathematically. Our signal processing research team is developing mathematical models to help us study the effects of compression on signals in noise. We can use these models to understand all 3 of those quantitative distortion effects. Before we dive into models and theorems and proofs, let's take a closer look at dynamic range compression. In most hearing aids, the signal is first split into several frequency channels. Within each channel, an envelope detector tracks the level of the signal over time. The envelope usually increases faster than it decreases, so the hearing aid can suppress sudden loud sounds without changing the gain too much during brief pauses. Next, that envelope is used to determine how much gain to apply to the signal. A compression curve relates the output level to the input level. For example, with a compression ratio of 3:1, the output level changes by 1 decibel for every 3 decibel change in the input level. Now let's see what happens when we have more than one signal. The filter bank is linear, so the filtered mixture is equal to the sum of the filtered component signals. That means that we can analyze the system in each frequency channel independently. Both the envelope detector and the level-dependent amplification are nonlinear processes, and they interact with each other, so they're hard to model mathematically. But if we make one simplifying assumption, we can separate their effects and create a useful model. That assumption is that the envelope of the mixture is the sum of the envelopes of the individual signals. While that's not true for particular signals, it is true in an average sense, if we think of the envelopes as being the energy of the signals. With this assumption, the envelope detector acts independently on each signal in the mixture. Now we can analyze the system in terms of the envelopes of the inputs and the envelopes of the outputs. The distribution of those envelopes depends on the number of frequency channels and the time constants of the envelope detector, but we don't need to worry about those parameters to understand the causes of distortion. The three distortion effects I mentioned earlier can all be derived from the compression function acting on the mixture of signal envelopes. Now let's look at the effect of compression on each individual signal envelope. We can calculate the gain based on the level of the mixture, but apply it to the signals separately to find their levels in the output. The output level for each signal is a function of both input levels, so there are multiple compression curves depending on the noise level. We call this relationship the effective compression function, and it's the key to analyzing the effect of noise on compression systems. Okay, now we're ready to do some math. Let's start by formally defining the compression function that relates input levels to output levels. Hearing aids use all sorts of compression curves, so we will use a broad definition. A compression function has non-negative power levels as its inputs and outputs, is non-decreasing, and is concave, which ensures that the output increases more slowly than the input. Now we can define the effective compression function, which describes how one signal is compressed in the presence of another. We calculate the gain from the sum of both signal levels, then apply that gain to the first signal. I'll use the effective compression function to derive those three nonlinear distortion effects. The first effect has been called a cross-source modulation. For two unrelated signals, like the sound of my voice and the sound of this pot, the envelopes will be mostly uncorrelated, as you can see from these samples. But after we compress them, they become negatively correlated. When one signal gets louder, the other gets quieter. We can prove this effect by treating the levels as random variables. Suppose that the input envelopes are statistically independent. The output envelopes are given by the effective compression functions of each signal in the presence of the other. Because the effective compression function is non-decreasing with respect to one signal and non-increasing with respect to the other, we can show that the covariance between the output levels is less than or equal to 0. The stronger the compression we apply, the stronger the effect. The second distortion effect is weaker effective compression. For example, if we design a system with a 3-to-1 compression function, but the dynamic range of the speech only shrinks by a factor of 2, then its effective compression ratio is 2-to-1. Why might that happen? Well, if the background noise is louder than the signal, then the gain will be set based on the noise, and it won't change as the level of the signal changes. Mathematically, we can define the compression ratio as the inverse of the slope of the compression function on a logarithmic scale. The steeper the slope, the less strongly the signal is compressed. Using the properties of concave functions, we can prove that the slope of the effective compression function is larger than the slope of the nominal compression function, meaning that the effective compression ratio is smaller. The effect is strongest when the noise is louder than the signal of interest. That means that when I'm trying to have a conversation in loud noise, my hearing aids aren't actually compressing the speech of the person I'm talking to, they're compressing the background noise. The third effect is on the long-term signal-to-noise ratio, or SNR. Researchers have found that the SNR can go up or down after compression, depending on the type and level of noise. If I'm listening to two speech signals, the quieter one will be boosted by more than the louder one, so their average levels will move closer together. If I'm listening to speech and low-level noise, like this fan, the fan noise will be boosted in between pauses in the speech, so on average it will get stronger. We can prove that when a time-varying signal like speech is mixed with noise that has constant level, the average signal-to-noise ratio always gets worse. This proof requires some extra technical assumptions about the compression function, and it relies on the fact that the effective compression function is concave in one signal and convex in the other. We can use Jensen's inequality to relate the average levels at the output to the average levels at the input. For steady noise, the average SNR is always worse after compression. Here are some examples of input and output signal-to-noise ratios for speech and white Gaussian noise. The noise boosting effect is strongest when the noise is weaker than the signal of interest. It's also stronger for larger compression ratios. The proof does not apply to other types of noise, like competing speech signals, but empirically, compression seems to hurt the long-term SNR if it was high to begin with. We've seen that compression can interact with noise in three ways, depending on the level and type of noise. If the two signals have similar levels, then they will modulate each other, creating distortion. If the noise is stronger than the signal of interest, the hearing aid will respond to the noise level and won't change the dynamic range of the signal. If the noise is weaker than the signal, compression will reduce the average signal-to-noise ratio. Using our mathematical model, we've shown that all three effects are consequences of applying a concave function to the sum of multiple signals. The more we compress the signals, the stronger the distortion. Is there anything we can do to avoid distortion when we use dynamic range compression in noisy environments? Well, the problem with hearing aids is that compression is applied after the signals are mixed. That's not true in music production, where mixing artists apply different processing effects to different instruments or vocals before adding them together. What if we could apply compression to each sound independently, or to some sounds but not others, or even compress different sounds in different ways? What if I could reduce the level of this pot while boosting the level of my voice at the same time? A few engineering researchers have proposed hearing aid compression algorithms that act more like music mixing. In one approach, the hearing aid switches back and forth between a fast-acting speech compressor and a slow-acting noise compressor, based on whether it thinks the speech or the noise is stronger at that moment. Our team has proposed using multiple microphones to separate sounds coming from different directions, so that we can apply different compression to each one. This approach works even for simultaneous sounds. Here is a simulation of multi-source dynamic range compression of 5 simultaneous talkers, with mild compression applied to one talker and more aggressive compression applied to the others. The hearing aid separates the speech signals using wearable microphone arrays. The multi-microphone method improves performance on all 3 distortion metrics, especially signal-to-noise ratio, compared to a conventional compression system. Larger microphone arrays provide better performance because they are better able to separate the speech sounds. Engineers are just starting to explore new strategies for improving dynamic range compression in noisy environments. We will need help from hearing researchers to understand how people hear in those complex situations. If we could compress different sources separately, should we? How should we set their dynamic ranges? And how do we measure how well it's working? If we can answer those questions, we might be able to design better compression systems that can handle multiple competing signals. Improving dynamic range compression would make hearing aids more useful in noisy situations, where people with hearing loss need them the most. Thank you for watching. If you'd like to learn more about our research team, please visit the Illinois Augmented Listening Laboratory website.